Hello, my name is Joseph Perez, and I am part of the environmental monitoring system that was proposed as our final project in our class for Intro to Electrical Engineering. And the rest of the videos are each teammates and what they proposed and gave to the project. Thank you.
Here is a slide for a block diagram for the EMS instrument. And if you noticed, everything goes into the NI real FPGA microprocessor, and it also comes out. All the digital data, signals, all come out from the microprocessors as well. And in this case, the NI MyReal will receive the analog data through analog input pins. In this case, we use pin 3, pin 5, and pin 7. Each one is receiving different analog data. For example, one is from the ozone sensor, the other one's methane sensor, and with ammonia sensor. We also have a on and off switch which controls the, the on and off state of the EMS device. Uh, the the FPGA is responsible for once it's powered on, it's responsible for power on the 5-volt fan and the the LEDs. So when the FPGA microprocessor sense that detects there's a certain level of toxic gas in air, it was starts sending signal from green to yellow and to red. And once it's in red, it will also sound alarm through the 5-volt speaker. For the bill of materials of the EMS instrument, it consists of a switch slide, which costs $3.81, and we have a ready to go a plastic box, which we just need to cut, the top portion and drill holes for the switches and LEDs and speakers and etc. We want to utilize two fans, 120 millimeter fans. So one will take air in, and the other one will flush internal air out. We will include a speaker, a small profile speaker with a system, and there is also a power barrel connector involved, which connects the FPGA and my real microprocessor. We want to get a cable assembly, so this one is installed internally, which connects to the power barrel, which gets the power input, external power input from the wall plug. And for the sensors, we have a ultra low power analog sensor module, and it is for sensing ozone gas. And this one costs $50. The next sensor that we will have to purchase is a methane gas sensor, and this one is less costly, but it functions quite well. Okay, and then let's move on to the last sensor that we are utilizing for the EMS instrument. It is a mini NHC ammonia uh, sensor, and this sensor costs $578 currently. And we looking definitely will look for alternatives when others are available. And then for the fans, it's a 5-volt DC fan. Okay, and we will have to purchase LEDs, green color LED, yellow, and red, with 3 each. And then those items that we already have as class materials are MyReal-1900, which we don't need to purchase additionally. And since we're utilizing a handheld digital multimeter for calibrating the sensors, so I'm including that here. And it's a good sensor. It's a good multimeter anyhow. For the LabVIEW software, it's available with this course, but I'm including it here just to let you aware that the cost of the LabVIEW software is actually $2,999, and it's the biggest portion of this project. And lastly, I want to add a laptop, which we will be utilizing throughout the duration of this project. And the total cost of the bill of material is $5,462. But with those items such as the MyReal, the multimeters, software, excluding the laptop that we already that are already in our possession, the cost of the project is just under $1,000. Here is a slide introducing ozone gas, and to explain why we want to include an ozone sensor in the EMS system. Ozone is a highly reactive gas, and it's composed of 3 oxygen atoms. Ozone are formed with chemical reactions between volatile organic compounds and nitrogen oxidized compounds. So when you sense the ozone, there's already a bunch of other toxic elements that's already within the environment. So the biggest contributor of ozone currently is coal-fired power plants. There's when you sense a high concentration of ozone in ambient air, then usually it's a sign of a bad air quality. So, so the health effect of the ozone on regular people is that the risk from breathing air containing ozone could lead to pulmonary diseases for children and for older adults. Let's talk a little bit more about the ozone sensor and why we're using this particular module in our EMC environmental monitoring system. The measurement range for this ozone sensor is between 0 to 20 part per million, and it has a good resolution at 0.1 part per million. This ozone sensor is compatible with NI MyReal microprocessor because it takes an input voltage of 3.3 volt. The spec sensor will output analog signal starting from 1.65 volt. So at 1.65 volt, it means there's a 0 ppm of ozone in the air. This sensor is easy to use because its output is in linear relationship with the ozone concentration in part per million level. So at 1.65 volt, the ozone is detected and read as 0 ppm. When FPGA sensed the analog voltage of 2.2 volts, it translates to the system, and that the ozone is currently at 6.67 part per million. And when the voltage, analog voltage is at 2.75 volts, the ozone is now at 13.3 ppm. And when the FPGA microprocessor detects a 3.3 volt, it's already at the maximum level of 20 parts per million of ozone in the air. Here is a software's flowchart for the ozone sensor. It starts with on and off switch. So once the system detects an on signal to the FPGA, the 5-volt fan will turn on. The FPGA will power the 5-volt fan first, and then it will start receiving the analog signals from the ozone sensor, which is in this block. And once the analog signal is in, the LabVIEW software will start calculating the concentration of the ozone internally. So when the FPGA detects 2.2 volts or less, it will output a signal to the green LED. So the green LED will be on, and it will go through the loop continuously until it goes back to this stage where the analog voltage is greater than 2.2 volt, but still is less than 2.75 volt. Then the yellow LED will come on, and the loop continues, and it goes to this stage where you'll be checked. The voltage will be checked again. So when the voltage is analog voltage is greater than 2.75 volt, two things will happen. The first thing is the red LED will begin to show up. At the same time, the 5-volt speaker will sound alarm to notify the immediate personnel that the dangerous level of ozone is currently present in the ambient air. So if none of these conditions are met, then no LED will come on. And this consists of the software flowchart for the ozone sensor.
Now, for one of my responsibilities for this project was the deliverables, mainly trying to find and acquire the components for the EMS, mainly finding the LEDs and the sensors and getting that so then we can come together and construct the EMS. Next, I'd be responsible for burning the programming for our EMS onto a CD so then it would be able to run, and everyone that either purchases it or uses it is able to use this device properly. It would run on LabVIEW Runtime Engine 8.5, which it would need to run with. Next, I would make sure to construct a technical manual. This is just giving the owner or the user an idea of the properties and programs that are in the CD-ROM just to use it. And then the product brochure, I'll also make sure that that is done as well, to have just information on where to find it or where to purchase it and other technical data. And then the specification sheet will ensure that the user would have all the specs and everything that they need to ensure that this is a product they are requiring or needing for their project. Next, for my portion of the project, I would be focusing on methane. Methane is an odorless, colorless, flammable substance. Usually you would see this natural gas in nature, decomposing areas or landfills or livestock, which would have that. Methane is explosive, so if it has a certain percentage of volume in a given area, it is more liable to explode and ignite. Such areas that you would see this are in mines when they're looking for those substances. So that's where a good area to have this EMS would be. So for the sensor that we acquired would be the MQ-4 gas sensor. It's a low-cost sensor from the Winson electronic company, and it's highly sensitive to methane, so it's able to pick it up pretty easily with no problem. It is also compatible with LabVIEW, which would be the main programming instrument that we'd be using for that. Its detection range is between 300 to 10,000 particles per million, and the voltage requirement is 5 volts at the max, either AC or DC. So next, now this is the flow chart, which is mainly the way the program would read. First off, we would start with an on and off switch just to start the system, which would activate the fan, which would draw air into the EMS. It would be placed in areas that it would have the need for it. So this is just to help to get the particles in there, so to sense it properly. The analog in would most likely be the sensor, so then it would get that information, and through our program it would calculate the concentration at which it would let us know depending on the LED lights. So first off, we'll be starting with the green LED. It'll be programmed to start registering between the 300 parts per million. So that would just be green. So then nothing would be arise. And once you start getting into the yellow LED with pin 19, that'd be roughly 350 particles per million. And then you can also see that the voltage is also increased. Once it starts getting closer to 400 particles per million, that's where the red LED will light, and then the speaker will also activate, letting anyone in the vicinity know that the levels of methane in the area are becoming too high for explosions to occur, and that's where it would keep on going.
Hello everyone, my name is Eric Beagle and I am a part of a group with Jimmy and Joseph. We'll be doing the EMS or environmental monitoring system. Unfortunately, I do not own a webcam and my computer does not come with a built-in one, so I will be just doing an audio and visual presentation with my slideshow. My responsibility in this project is the task list and the ammonia sensor. So starting off with the task list, in week 1 we're looking at a design review. Week 1 and 2 we're looking at project planning and preparation. Week 2 and 3 we're looking at a LabVIEW simulation. Week 4 through 6 we're looking at our schematic simulation. Week 7 and 8 we're looking at a PCB design. 8 and 9 we're looking at the ship off our bill of material to gain our parts. Week 9 we're looking to populate our PC board. Week 10 and 11 we're looking to troubleshoot prototype. Week 3 through 11 we're looking to complete our EMS software. Week 12 is our EMS assembly. Week 13 is our test EMS. Week 3 through 15 we're going to be continuing to build upon our technical manual, and week 14 and 15 we will be doing both product brochure and spec sheet. By week 16, our 4-month mark, we should look to be completely done with our project and approved and ready to go out and deploy into factories, businesses, and homes wherever necessary. Now the compound I'm going over is ammonia, NH3. It's an inorganic compound. It consists of nitrogen and hydrogen. Now if you all are familiar with ammonia, it is very strong, it's very pungent, and in concentrations larger than 25 parts per million, you begin to smell the ammonia, which is comparable to cat urine. It is very dangerous. It burns the eyes, nasal cavity, and the lungs, and it an exposure to 50 parts per minute or more, at this point is when it becomes very dangerous, and is when we would alarm our occupants of a dangerous situation and to evacuate the building. My ammonia sensor that I am providing for this project is the ammonia sensor. It is a model number MQ137. The ranges are a 5 to 500 parts per million, and our 5 volts AC or DC is our input power. It has a very high sensitivity to ammonia, and it is microprocessor compatible. Therefore, you can utilize it with an Arduino, you can utilize it with a Raspberry Pi, or in this instance, we're using a National Instrument MyRio and a LabVIEW software. We'll be using LabVIEW to build our program and our block diagram to control our unit. Now, the software flowchart kind of describes in order how the process of this machine is going to go. Our on-off switch will be hit, which will send the digital input to pin 18 and input 11 to start our fan. Our fan will, in essence, bring in outside air into our unit for testing. Based off testing, we will bring in an analog input into our National Instrument MyRio on pin number 7 on analog input 2. That will consist of a 4 to 20 milliamp reading, whereas 4 is 0, 20 is 500 parts per minute, or excuse me, parts per million. Anything at 10 or below, we're going to send a signal to have our green LED, meaning air quality is okay for occupants to be in. Anything that is between 15 and 10 and 15 is going to be a yellow. It's going to be a caution indicator to let people know that the air quality is a potential issue for people with respiratory illnesses, asthma, and so on. And anything above 15 milliamps will be an issue, and at that point a red alarm would be instated, and a audible alarm as well through a 5-volt speaker to let people know this building is not safe and to evacuate. In this presentation, I utilized out of the AMU library an article titled Ammonia. It was copyrighted in 2014. It was obtained through the web on AMU library. Thank you.
And that is our project, the environmental monitoring system that we proposed for our final project. As we said before, it would cover monitoring ozone, methane, and ammonia, and we went over those areas. Depending on how the project goes, we might need to adjust here and there, but this is our generalized plan if we were to implement it for an actual final project. Thank you very much and appreciate your time. Bye-bye.